Today we're going to talk about hypothesis testing. So we haven't entirely finished our topic of probability. We're going to move back to probability after we do some more work on hypothesis testing. But we're in a good position with having seen the box model and particular probability distributions to now turn to the topic of hypothesis testing, and then we'll get back and wrap up with another lecture or two on probability next week. All right, this is one of the readings that you have for the course. It's towards the back of the reader. The reading assignments, just as a reminder, they're all posted. If you click on syllabus, I add to the reading assignments weekly. So this is one of the chapters in Statistics, A Guide to the Unknown by Cobb and Gelbach. It's called Statistics in the Courtroom, United States versus Kristen Gilbert. So here's Kristen Gilbert. This is actually a mugshot of her when she was arrested. She was born in 1967 in Fall River, Massachusetts, and she was a very talented student. She graduated high school at 16 and went on to the Greenfield Community College and received a certificate to be a registered nurse in 1988. Then in 1989, she joined the Veterans Administration Medical Clinic in Northampton, Massachusetts. She had established a very good reputation for staying calm in stressful situations. This is a picture of the VAMC, the Veterans Administration Medical Clinic, where she worked. She had, within a year of being hired at the VAMC, she was featured in their magazine as a top nurse. And in particular, when a patient would go into cardiac arrest, she would sound the code blue alarm, remain calm, and administer a shot of epinephrine, which is a synthetic adrenaline, to restart the heart. But by the mid-1990s, about 95, 96, there were suspicions that were raised by the other nurses at the VAMC. It seemed that too often there were code blues on the shifts where Gilbert was working. So they raised their concerns, and an initial VA report found that the number of deaths were consistent with patterns at other VA hospitals. The staff remained suspicious and went again to the administration and expressed their suspicions. And as a result, the administration hired a statistician to look into the pattern of deaths at the VAMC. They hired Gelbach, who was the co-author of this article, and his findings did agree with the staff concerns. So they then went on to bring this to make a decision as to whether or not she should be brought for trial. So in particular, the U.S. Attorney General, Welch, convened a grand jury in 1998 to hear evidence against Gilbert. And so what we're going to be looking at this morning is the evidence that was presented to the grand jury and then for the pretrial. So just a little bit of background in terms of how the U.S. court system works is that a grand jury is a jury that looks at the evidence to see whether or not there's enough evidence and enough suspicion that something might have gone wrong to indict someone and have a trial. So the grand jury determines whether there's enough evidence to go on to have a trial. And Gelbach's statistical analysis played a crucial role in the evidence for the decision-making process to bring Gilbert to trial. So there were essentially four sources of evidence that were considered. The first one was whether or not Gilbert would have any motivation. She had a good paying job. She was very good at her job. And why would she want to do this? And essentially what was argued was that she enjoyed the thrill of a crisis. She needed the recognition. She had at that time, she had a boyfriend who also worked at the hospital, and she wanted to impress him. And so that was considered possible motivation for creating these crises. And unfortunately, several people died from these crises that were created, or potentially created. So there was also a second piece of evidence, was testimony of the coworkers. And essentially, their testimony was that Gilbert had access to epinephrine. So it's not that any of them actually saw her administer it. The third one was the testimony of a physician about the symptoms of the people who had died. They were all roughly middle-aged men in pretty good health, and they were not the typical candidates for cardiac arrest. So those were 3 of the 4 pieces of evidence. And then the fourth one was statistical in nature. And it was considered to be quite crucial to the decision of the grand jury to go on and have a trial, because no one had actually seen Gilbert do anything wrong. So I'd like to show you some of the evidence that was presented. So the question is, were there so many excess deaths when Gilbert was present, so on her shifts, as to be suspicious in the eyes of science? So the eyes of science as opposed to the eyes of her coworkers. So can we bring some sort of scientific process to examining the number of excess deaths? The excess meaning the number of deaths that exceed what you might expect on a regular shift. So were there so many excess deaths when Gilbert was present as to be suspicious in the eyes of science? So Gelbach had 3 pieces of his testimony. The first one was to look at the pattern of deaths and examine them by shift and by year. So Gilbert had worked there for about 5 or 6 years. And if we look across at the pattern of deaths on different shifts and for different years, and was it the case that there was something that looking somewhat suspicious or unusual in the shifts in which Gilbert worked? The second piece of his testimony was about variability in a chance process. So this wasn't specifically any chance process related to Gilbert's work, but it's just to prime the jury, a grand jury, to understand how to interpret the next piece of his testimony. And that's the statistical test for whether the pattern linking the excess deaths to Gilbert's presence on the shift was so extreme as to be regarded, was too extreme as to be regarded as ordinary expected variability. So these 3 pieces of his testimony are related to the first 2 is the 2 of the things that we've studied so far in class, and then the third one is what we're starting today. So the very first one, this pattern of death, is what we were doing at the beginning of the semester in terms of an informal analysis of the data. So in our informal analysis, we were often trying to make comparisons and examine variability to see if there's any unusual things going on. So that was number 1 of Gelbach's testimony. Number 2 was looking at the variability in the chance process, is what we've been doing for the past week or so in terms of simulating a random process like a coin toss or taking cards from a deck, seeing what we might expect and calculating the chance of having some really rare event or not. And then finally, having a more formal statistical test is what we are just now starting to examine. And what can you conclude from this formal statistical test? All right, so let's look at number 1 on his list, the pattern of deaths. So he created a set of bar charts, and I used what we've learned so far at the beginning of the semester on making nice plots, and I replotted what he did. And The plot shows data taken from the VAMC. And so I'm going to describe it before I actually show it to you. Each point in this plot represents the number of deaths over an entire year for a particular shift. So there will be 3 points for each year. There were 3 shifts. The first shift was the night shift, which started at midnight, went till 8 in the morning. The next shift was a day shift, starting at 8 in the morning and going to 4 in the afternoon. And then the final shift was what is called the evening shift, which started at 4 in the afternoon and went till midnight. So we're looking at the total number of deaths in a shift over the entire year for several years. And they've been color-coded. The shifts in which Gilbert worked have been color-coded as red. So Gilbert started on the night shift in March of 1990 and then was moved to the evening shift in the following year and remained in the evening shift until she left on medical leave in early February of 1996. And this was right when the staff said, we're still suspicious, we think there's something going on. So now I'm going to present the plot to you, and I'd like you to take a look at it and see what you think. So I've connected the dots for each shift. The blue lines connect the dots for the night shift, the green ones for the day, and the dark orange for the evening. So if we look at 1988, we see that there were about 10 to 15 deaths per shift for the entire year, for each shift. So what do you think of the variability? Yeah? Oh, that's a really good statement. It's hard to say whether Gilbert caused them or not. We're actually not looking at causation here. We're looking at whether or not there's an unusual amount of, we're looking at the variability to see whether there seems to be something unusual going on in the shifts in which Gilbert worked. Okay? This is, so the grand jury is deciding whether or not there's enough reason to suspect something might be going on to go to trial. What do you think? You see where the red dots are? There are 1, 2, 3, 4, 5, 6 red dots. Now, in fact, Gilbert was still working in 1996. I did not color it red because she resigned in February of 96. So we see 2 sets of dots in 1998 and 1999 before Gilbert was ever working there. And roughly the number of deaths is in the 10 to 15 range. And there's some variability. That's, you know, the range is about 5 or so. And then in 1989, it's similar. After Gilbert left, if we go back and look, or go over and look at 1997, we see that the pattern in the variability of deaths on those shifts sort of goes back to where it was before Gilbert was ever hired. So it's actually somewhat lower than in 1988. And the blue and the green in the middle range is roughly consistent with the number of deaths that we see in all 3 shifts when Gilbert was not working. So it does look like the shifts in which, the evening shifts in which Gilbert was working at were farther away from the main typical expected number of deaths in a year on a shift. Were you going to say something?
I thought it would be nice if she had worked different shifts during the year, but that cannot. That would be
Well, it would be nice if she had worked different shifts during the year. What would be ideal is if they had assigned her at random to different shifts, and then you could really draw some strong conclusions. But unfortunately, that's not how it happened. So there's a clear pattern associating Gilbert's presence with excess deaths. However, this pattern might be nothing more than the result of ordinary expected variation. So the next part of Gelbach's testimony was to say, well, what's a typical kind of thing that might happen on these shifts? And before going there, he decided to prime the jury with just talking about something that they might be really familiar with. So he talked about coin tossing. So he talked about the familiar way of tossing a coin 10 times and keeping track of how many heads you've seen. Now, we've studied that just last week. In fact, on Friday, we named that distribution as the binomial distribution, and we had computed, or we derived a function to compute the probabilities of a certain number of heads in a flips of a coin toss. So essentially we're saying the coin could land heads or tails with a chance 50-50. If you flip a coin 10 times, how likely is it for you to see 10 heads in 10 flips of a coin? So this gets at, well, what do we expect to see in 10 flips of a coin? So what do you expect to see in 10 flips of a coin? How many heads do you expect to see in 10 flips of a coin? 5, right. You expect to see 5. Does that mean you're always going to see 5? No, there's some amount of variability due to this chance process. So we can actually answer the question of, well, how likely is it that we would see 6 or more heads when we flip a coin 10 times? We've got our binomial probabilities, and we can compute the chance and say 38% of the time we would expect 6 or more heads. So it's very likely to see 6 or more heads when you flip a coin 10 times. The d-binom function can compute those probabilities for us, or the p-binom can do the cumulative probabilities for us. So if we look at the results from the d-binom, you see that there's exactly 6 heads has a probability of 0.21, exactly 7 heads, 0.12, exactly 8 heads, 0.04, exactly 9 heads, 1%, and exactly 10 heads, 1 in 1,000. So the chance that you see 9 or more heads is about 11 in 1,000, or roughly 1% of the time. The chance that you would see 10 heads is really quite rare, like 1 in 1,000 times. So 1 in 1,000 times you would expect to get 10 heads in 10 flips of a coin. So then the question is, if this actually happened, if someone pulled a coin out of their pocket, flipped it 10 times, got 10 heads in a row, what would you do? What would you think? What would you decide? You might decide it was biased in the sense of maybe there are heads on both sides of the coin, right? That would be really biased. Or that somehow there are people who know how to flip coins so that they can flip it to land exactly the way they want it to. So you might be suspicious of the coin flipper. You might be suspicious of the coin. Or you might say, wow, I guess I've just seen an event that happens in roughly 1 in 1,000 cases. So at some point, you get past when you see something really rare, you say, you know, I've seen something really rare, so I don't believe anymore that this is the chance process that I thought was going on. I'm going to reject that chance process and say, I think there's something going on here aside from chance. And that could be a biased coin in this case, or it could be someone who really knows how to flip a coin so it lands the way they want it to every time. So you would be justified in thinking that there's something going on besides just chance variation. And that's when you've seen something that's so rare that you start to doubt the underlying assumptions that you made in this chance process. So now that Gelbach has sort of primed his audience, the grand jury, he then moves to the next stage, which is to perform an actual statistical test, which is a hypothesis test for Gilbert's actual data. So remember, he was called in by the VA hospital when the staff said, okay, the VA administration said that the excess number of deaths doesn't seem atypical from other VA hospitals. So he was pulled in and he decided to look at just the 18 months leading up to February 1996 when Gilbert went on medical leave. So there were 547 days in this 18-month period, and there were three shifts each day, so a total of 1,641 shifts. So then he got hold of every shift that Gilbert worked, and he kept track of two things. One was, for each of these shifts, he kept track of two things. One was whether it was a night shift, day shift, or evening shift. And the other was, sorry, that was, of course he had that, but that was not, there was two more things he kept track of. One was whether or not there was a death on that shift, and whether or not Gilbert worked on that shift. So those were the two variables that he measured. And let me ask you this, what kind of data are these two variables? There is nominal, ordinal, ratio, and interval. What kind of data or measurements are these two pieces of information? Yes? Nominal. So, and in particular, Gilbert worked on the shift, yes or no? There was at least one death on the shift, yes or no? So in particular, there are only two levels for each of these nominal variables. How many observations were there in this data set? How many cases was he looking at? How many records? So if you had to make a data frame, how big would that data frame be? How many rows would there be in the data frame? Yes? The total number of shifts, 1,641. That's right. So I'm just trying to connect it back to what you've seen before. This would be a data frame with 1,641 rows. And what two columns that we're interested in are, was Gilbert on the shift? Was there a death on the shift? And so with nominal data, what we typically do, well, you tell me, what do we typically do with nominal data like this? How would you analyze it? What would you do? That was that's a very good point. That's your step ahead of me. So you're saying I would think about the underlying model and whether or not it follows a binomial. That's a good point. But if you had the data at hand, what would you do? What would you do with these data? Would you make a scatter plot of these data? Would you make a density plot of these data? Yeah. So you're saying you might consider a box plot for the 3 different shifts and so what's the observation what's the variable of the I know now you're telling me what's the x-axis would be type of shift and what would deaths. So that's a good idea if I actually had the number of deaths. I don't have that. I just have the nominal, was there a death or not? So making box plots of 0, 1, or 2 level doesn't quite work. What else might you do? What would you do? Yes?
I would make
A strip chart? I think that has the same problem as what, is it Dave? Nick. What Nick was saying is that it's just remember, it's just nominal data, right? And so a strip chart, it would be 0 or 1, and they'd all just be plotted on top of each other. Somebody else? Yes? We could make a table, that's right. And and the table would be, according to this, one variable would be the columns, and the other variable would be the rows. Death, yes or no, or at least one death, and was Gilbert working, yes or no. And we would be what? Doing what? We were tabulating the results. We'd be counting up all of the shifts where there was a death and Gilbert was working, where there was a death and Gilbert wasn't working, where there were no deaths and Gilbert was working, and where there were no deaths and Gilbert was not working. That's right. And what's one thing you could do with a table once you have it? This is good. It shows I've broken you of the habit of what you were all doing with your data analysis at the start of the semester. No one's saying you'd make a bar chart. That's good. You might make a mosaic plot or a bar plot. But, in fact, you could just as well make a table, which is what you said. So here's the table. Death on the shift, yes or no? Gilbert present, yes or no? So Gilbert worked how many shifts in this period of time, this 18 months? How many shifts did Gilbert work? I heard you, 257. How many deaths were there, how many shifts had a death, at least one death on it in this entire 18-month period? 74, that's right. Of those 74, how many of those shifts was Gilbert working? 40. Does that sound like a lot to you? So she was working on 40 of the shifts where at least one person died. Yeah? She only worked? Very good observation. If you look at how often was she working, she was working on 257 out of the 1,641 shifts. That's what, about 1 in 7 shifts or so? And how many shifts of the ones where someone died? She was on more than half of them. So that should be somewhat suspicious. What we're going to do is we're going to say, we're going to sort of calculate how likely that might be. So the table summarizes the records. In the 1,641 shifts, there were 74 shifts for which there was at least one death. On 40 of those 74 shifts, Gilbert was working. Is that more than you would expect? So to answer that question, we need a model for how things might have happened. Yes?
When you say Gilbert wasn't present, does that mean like all the other nurses?
Someone else was on the.
How many other people were?
That's a very good question. This is Gilbert's working, but she's only one nurse of many nurses. There was definitely more than one nurse on the ward in which she was working. So
You don't know how, like, I mean, it would be, like, if there was one other nurse, maybe that would,
I don't have that information. Yeah, and that's a really good point. You're already going to thinking about, well, what can we really say even if this is an anomaly? Because there were clearly more nurses on the shift, on any shift, than just Gilbert, right? And we're going to get to that. So if you had to describe the, if you were here's this devil's advocate, or if you were on the side, in this case, on the side, if you were on Gilbert's side, and what would you say? How would you argue against, how would you try to reason about these 40? Yes? That's a really good point. Most of her shifts are in the evening, and maybe that's when these sort of stressful cardiac arrests, maybe the doctors aren't as likely to be present. Things could happen. But that, again, is going, you're one step ahead of me. Just like, is it Sharad? Is that? Sharada was also. You're one step ahead of me. You're already explaining why this might have happened. And I'm actually looking for a probability model that says, well, this could have just happened by chance. So let's back up a little bit and say, how could this have happened by chance? Give me a model, a probability model, a null model for how this might have happened by chance. So think of the outcome on a shift as a draw from a box without replacement. The box has 74 tickets in it marked 1 and 1,567 tickets marked 0. So when the nurses show up for their shift, one of them draws a ticket out of the box, and if it's a 0, no one dies on that shift. If it's a 1, at least one person dies on that shift. So what it's sort of saying is that those deaths, those 74 deaths, would have happened whether or not Gilbert was present on them. It's just by chance that she happened to be present on so many shifts when someone died. A slightly different model, so that's the one box model, slightly different model was already raised, which is more like the coin tossing model. It could be that you show up for a shift, someone tosses a coin. If it lands head, there'll be at least one death on the shift. That probability would be not 50-50, but given what we'd seen, we would estimate that probability to be 74 out of 1641. How is that different from the model I just described? That's also a box model. What's the difference between the two? Yes? That's making draws and putting them back each time. And you could argue either way. They're both legitimate models, box models for this process. So we're going to go down the route of drawing without replacement. So Gilbert shifts are like 257 draws from the box. That's our model, draws without replacement. So how likely is it to get at least 40 of the, I think that's, how likely is it to get at least 40 of the 74 cards that have a 1 on it in the 257 draws? So that's the question that we're trying to answer, is like how rare of an event did we just see, assuming that whether or not there's a death on the shift is like draws from this box. I used R to compute the exact probabilities. Do you guys remember what the distribution is? We covered this on Friday. Hypergeometric. So there are two types of tickets, the 1s and the 0s. we're drawing without replacement, and we're counting up how many ones we see. That follows a hypergeometric distribution. These are the exact probabilities computed in R for the hypergeometric distribution. What do you see? Here's 40. So to see 40 or more deaths has a chance of, if I've computed it correctly, less than 1 in a trillion. What we expect to see is that there's roughly 4.5% of the tickets in the box are marked 1. So of the 257 draws, you'd expect to see roughly 10 or 12 shifts of hers that had a death on the shift. So we've seen something really, really rare. So the grand jury found that the statistical evidence was persuasive, and Gilbert was indicted. The VA hospital is, because it's owned by or is property of the federal government, it did not fall under Massachusetts state law. That meant that she would be tried in a federal court, a federal district court, and it was possible to be given the death penalty, even though in Massachusetts there is no death penalty. So we're now on to the second phase, and this is the trial phase, and there's a trial jury or a petit jury, and that hears the evidence in a trial as presented by both the plaintiff and the defendant. After hearing all of the evidence, the jury retires for deliberation, and they consider the verdict. In this case, a majority is required for a guilty verdict, and if they want to decide on a death penalty, it has to be a unanimous sentence, a unanimous jury. Now, when it comes to hearing evidence in a jury trial, the court system is set up so that there could be expert testimony or an expert witness. They call in the experts when there's some sort of evidence that's highly specialized, technical, scientific, that a jury might not be exactly familiar with. And so the point of having this expert witness is to help the jury understand the evidence. So the Supreme Court has set up guidelines to make sure that the evidence that's brought into the court is scientific and not unscientific. And a problem that often arises with bringing in expert witnesses is when one side hears about an expert witness is going to testify about a particular kind of evidence, then the other side will bring in their expert to testify and have the complete opposite conclusion. And so it can wind up where there's just a sort of a canceling out effect of the expert testimony. So the question is whether or not whether or not the trial jury should hear the statistical evidence that Gelbach testified to the grand jury. So you might think, why wouldn't they hear it? It's pretty important evidence. So the defendants brought in a statistician before the trial was to happen to write a report to the judge as to whether or not the statistical evidence should be brought in to the trial jury. And that was Cobb, who was the co-author on this article. Cobb addressed three things. The first one was the statistical analysis that Gelbach did, was it done correctly? The second one was, well, what does the probability calculation not tell you? And there are two parts to this. The first one is this notion of association versus causation, which you guys have already sort of brought up in this analysis. What are the conclusions that you can draw from this observational study as opposed to a designed experiment? And the other is this issue of the prosecutor's fallacy, which is how do you interpret that probability that we just calculated, that 1 in a trillion calculation? All right, was the statistical analysis done correctly? So the defense statistician Cobb actually agreed with all the calculations that Gelbach had done. He said that, yes, they did a good job. The calculations were done correctly. The excess deaths was an extremely rare outcome. And therefore, there's a justification for the indictment. We don't believe that it was really just an outcome due to a chance process, to random variation. Now, what about the next argument of association versus causation? So far, we've only looked at so far what you've seen when we've been talking about how rare is it that something could occur. We've been looking at well-designed experiments. In fact, we talked about, with assault trials, the difference between using the first graders and third graders as controls versus the other experiment where they took all the people, all the children whose parents consented and randomly assigned them to treatment or control, and how those are really different. And the judgments you can make from the randomization are stronger than what you can from the first and third grader controls. So in a well-designed experiment, you've used randomization to try and even out things, and you've controlled for all these other potential factors such that when you see a difference between the treatment group and the control group, if you've done a really good job, if that difference is such that it's not likely to have occurred by chance, you can then conclude that, well, it must be the treatment. That's not the case here. We might have a really tiny probability, and we could conclude that, yes, it's not likely that chance variation produced that. There is a real difference, but we can't necessarily conclude that it's therefore Gilbert. I think you guys have already pointed out several cases of that. Sharada has said that, well, isn't there more than one nurse on the shift? And yes, that's the case. Someone else said, what about the fact that these are all night or evening shifts? Couldn't that play a factor? Yes? No, I don't know why, although there were 40 deaths on her shifts as opposed to other people's. But I'll say that there's one piece of the story that I have not told you, which was by the time she was a teenager, her relatives and friends had noted that she would lie about things and sort of make up situations that they clearly knew she was lying about. So there could have been other sort of personality factors going on that's not part of this story. Right. But I don't know. Yes?
Did they take statistics for the amount of people who had heart attacks, not just deaths?
That's a very good point. And I don't know the answer to it. So your question is, did they did they analyze people who went into cardiac arrest and did not die? And that would be a really good idea to look at. I don't know if they did or not. So the notion was that she was sort of inducing the problem or creating the problem and then trying to solve it. And it could be that it kept sort of ratcheting up and therefore some people died. And yes, as far as I don't know whether or not they did that analysis. Chances are they did, but it's not part of the report. So we don't have this designed experiment, and therefore Gilbert's presence on the ward, to have turned it into a designed experiment, we would have had to randomly assign Gilbert to different shifts on the ward, and then we would have a chance at saying, oh, these are random assignments, and it's really rare to have seen so many deaths on those shifts, and therefore I could conclude that Gilbert is the reason. But there could be other possible explanations given the way the situation was set up. And some of those you have already pointed out. So the last piece is the prosecutor's fallacy. And this is that we take a probability such as 1 in a billion or 1 in a trillion, and remember how we computed it. We computed it by saying we're assuming that there's nothing going on but chance variation. And so what's the chance we see something as rare as 40 or more deaths on the shifts in which Gilbert worked? That's a really important assumption. So what we're computing is the probability of seeing something as rare or even rarer on Gilbert's shifts, assuming that it was all just chance variation and there's nothing going on. Now, this logic says nothing about other possible causes. So when we reject that, we don't have anything that we're turning to. So here's the logic, the slippery logic that goes on, is that suppose Gilbert's innocent and the deaths behave in a chance-like way. The probability is less than 1 in a billion or 1 in a trillion that you would see so many deaths on Gilbert's shifts. The next step is logically correct. You should say if Gilbert is innocent, then it would be almost impossible to get so many excess deaths. The next step, which a lot of people fall into this trap, including the prosecutors and also including the jury, is to say with this many excess deaths, the chance is less than 1 in a billion that Gilbert is innocent. And that's not at all the chance that we've just computed. We have just computed the chance, assuming she's innocent, that we'd see such a rare event. You cannot turn it around to say, so in a way that's a conditional probability. You're conditioning on her innocence and saying there's a chance process. That she's innocent and there's a chance process. What's the probability of seeing something as rare as this? When you reject it, you're essentially rejecting the chance process. You're not saying, oh, I've now computed the probability that she's not innocent. All you've computed is that this is a very rare event, therefore I reject the chance process. So it was decided that it was too easy for the jury to fall into the trap of thinking of this probability as the probability of her innocence or guilt. And the statistician for the defense argued that therefore the statistical evidence shouldn't be part of it because we already were in the trial jury based on the statistical evidence which says you should be suspicious. The jury, however, looked at other evidence, and based on the other evidence, they found Gilbert guilty on 3 counts of first-degree murder and 2 counts of attempted murder. They voted for the death penalty 8-4, and therefore she was not given the death penalty and instead was given life in prison without possibility of parole. What I now like to do in the remaining 3 minutes is to quickly go through the terminology related to hypothesis testing that we just did. First of all, we start with a test statistic, which is some summary statistic of the data. In this case, the summary statistics was the count, the total number of shifts that had at least 1 death. Then we have a null model, which is a probability model for explaining the chance process for generating the data. Our null model was our box model that said Gilbert's shifts were like draws from this box with 74 ones in it. What's the chance that she got 40 or more ones in her 257 draws? The null hypothesis says that any deviation from what you might expect, which was about 10 or 12 shifts with deaths, any deviation from what you'd expect is simply due to the chance process. And we can compute that probability. That probability is called a p-value. The chance of an outcome is rare or even more rare than the one that we've observed under the assumptions of the null hypothesis and the null model is the p-value. And if the p-value is very, very, very small, we reject the explanation of chance variability. It says, wow, we've just seen a rare event. That is now casting doubt on whether or not my null model was correct. I now think that there's something going on. Now, depending on the circumstances, if we have a well-designed, controlled experiment, when I reject that hypothesis, I can say, oh, it must be due to the treatment. In this case, with Gilbert's situation, when I reject the null hypothesis, all I have is that there's something going on. What that is not clear. So we have not proven that the null is false. We have only rejected the null hypothesis. We no longer think that it is an adequate explanation for that the variability is an adequate explanation for what was going on. In some cases, we have an alternative hypothesis, which is an alternative to the null. In our case, our alternative is just the simple statement is the difference is real, or there is something going on aside from chance. Later on, we'll have much more concrete alternative hypotheses that we'll be studying. For now, we're leaving it at this. And that's it. See you all on Wednesday.